Okay, thank you for the introduction, and also many thanks to the organizers for the opportunity to talk in this nice conference. So I will start with a very brief introduction with atom laser. So what is an atom laser? The concept is very simple. It's the same as photon laser, but it's just replaced by atoms. So it's a coherent state of propagating atoms, which behaves like a wave. But the construction procedure is slightly complicated. So the atoms has to form a Bose-Einstein condensate, and then it has to couple with the light. It's a light and atom interaction kind of thing. And the working principle will be clear from this diagram. So here, suppose we have a two-level atom. One is in the G and the other is E. And the Bose-Einstein condensate is formed in the ground state. And that state is trapped magnetically, whereas the state E is untrapped, but these two states, G and E, are coupled via an optical light, which is, of course, has to be, the frequency of the light has to be of the order of this two-level system, gap of the two-level system. But then the question arises, why the atom laser? I mean, already we know the laser, and this is already very, very successful, so we don't need a replacement of that. The thing is that, well, it can be used wherever the usual laser is used, but we, of course, don't need that. But the thing is that it will give some accuracy, increased accuracy in interferometry. That's what, there are many papers on this, where they study that the atom laser can increase the efficiency of this interferometry, as well as in measurement of squeezing in the context of super dense coding and those things, these atom laser are used. So there are different ways to construct atom laser. The first one, well, of course, I have introduced one thing, is squeezed atom laser. Squeezed atom laser is nothing but this light is replaced by a squeezed light. In general, it was original some coherent state or whatever, but now the light we replace by squeezed light and we get a squeezed atom laser. And there have been some construction. One is by coupling the usual way, by coupling the squeezed optical beam with the Bose-Einstein condensate, and we get atom laser. And the second one, well, of course, with the first one there is a problem, because one has to construct a squeezed light of that particular frequency which is compatible with the gap of the two-level systems. And that is slightly difficult from the experimental point of view. So that's why people are trying to get some alternative ideas. And this is one of these idea where they constructed a car-type nonlinear interaction to get a squeezing kind of effects, which is obvious from the quantum optics point of view. And here there is a third one, which is the discussion of this talk. And I will just go through the construction procedure, how we can have alternative squeezed atom laser. But the question should arise at this point is that why squeezed atom laser should be interesting? Well, we know we have many talks in this conference from the quantum optics perspective. And we know that squeezing is very important in optical cases. For instance, they can reduce the noise in optical communications as shown in this figure, because this elliptical things is squeezed, one and the other one, the circle ones are coherent, and they can reduce the noise in the optical communications. But most importantly, the squeezed atoms or squeezed beam is used in quantum information theory, which is, I think, the most important applications. And obviously, the squeezed atom lasers would have the similar kind of opportunity or similar kind of advantages over the usual atom laser. Well, let's go for some of the technicalities slightly. I mean, I will go quickly. I understand that this is mathematics, but I mean, I will be quick with this sense. So we have the Hamiltonian, where this A dagger A, these are the creation annihilation operators for the light, for the, I mean, the ladder operators for the optical radiation field. And VE and VG are the ladder operators for the excited state and the ground state of the atom. And these two states are coupled via this matrix element, omega, which depends on epsilon naught and V is the effective mode volume, and epsilon is the permittivity of free space, and so on. With this Hamiltonian, it's slightly difficult to solve, so one takes some kind of approximations. Of course, the Bogoliubov approximation should be very nice in this sense, which means that we don't need to consider the change of the atoms in ground state, because the number of atoms in the ground state is very, very large. So we just consider, we just neglect that, and then we can replace Vg and Vg dagger, each of the quantities, by square root of Nc, so that we arrive to this Hamiltonian. Well, so now let's introduce a bit of generalizations of this optical field. What it means that we want to generalize this A and A dagger. So atoms remain same. That is the usual quantum mechanics, we keep it. But we generalize the radiation field. So we generalize A to A dagger, and I mean A to A and A to capital A, and this way. And the generalization is known as the nonlinear generalizations, where you take capital A to be small a times some function and so on, so that they can work on the Fock space in the usual Fock space. But one needs to just calculate this Fn. And this Fn will come from the model itself. Suppose we can factorize the Hamiltonian in terms of A dagger A, which is of this form of Fn, and then we know the eigenvalues, so that the Fn can be constructed from that particular model, and then we replace it in the system so that we get a generalized system. So I will use this trick to some model. This is an example. I've just introduced a model which is, let's say, the commutation relation is modified into this form, so that they can be, the observables capital X and capital P can be represented in terms of small x and small p, where this is the usual quantum mechanics. So that we have a harmonic oscillator in this space, and of course this is not Hermitian. Okay, so we use the standard techniques of the pseudo-hermiticity to get a Hermitian counterpart of this Hamiltonian by just having a metric operator which has been calculated in this paper. I mean, this is so what is important that we don't now look at this, but let's look at this, which is a harmonic oscillator Hamiltonian plus some nonlinear terms. I mean, there is a deformation parameter tau, which is coming from this signature of this deformed relation, and this is nothing but a nonlinear system. I mean, this is already. I mean, I think there has already been a lot of discussions regarding the nonlinearity, and that can be understood in the laboratory also that we are hearing. So it's nothing but a nonlinear Hamiltonian, and we can get the real eigenvalues and eigenfunctions, and all are consistent with this. So for this model, we get this Fn, which is, I mean, here was this A and B, and we just know this Fn and apply the generalization procedure and to get the generalized atom laser. So the Hamiltonian will be deformed according to this, because we have now A dagger A and all these small a replaced by capital A's, so that we have this Hamiltonian, and that can be solved by using some polarity operators, which are just kind of transformation of the basis. So we have the relations, commutation relations are preserved, but there is no harm to take this kind of transformation, and so that when we invert these relations, we get AT and BT in terms of these operators. And now we can replace it into the Hamiltonian to get the solution. And of course, we have to ignore some terms, which are the oscillating terms, M dagger N and N dagger M. This kind of approximations has been taken to solve this system. And we can solve the Heisenberg equations of motion. This is a pretty standard procedure, so we just replace the operators and get the solutions. And finally, we have the optical field in terms of these operators, theta m and theta n, which are slightly complicated in terms of mathematics. So anyway, we have the solution. Now we have to analyze and see whether this can give a nice physical system and gives a squeezing or non-classicality. So just to introduce the notions of non-classicality and squeezing, we know that there are many standard procedures, but here I have taken only two procedures. One is the quadrature squeezing and the photon anti-bunching. I mean, of course, I can calculate Wigner function or the other standard procedures, but these two should be enough. And for the squeezing to exist, we need these two conditions. I mean, either of one of these conditions has to satisfy. Delta y and delta z, they are, I mean, of course, the y and z are the quadrature operators that has been defined in terms of the A and A daggers. So these two conditions are basically equivalent to these two conditions. So if we just construct S1 and S2, and if we see that S1 is less than 0 or S2 is less than 0, that means the squeezing exists, we have, I mean, we can calculate those things if we know these commutators. Similarly, for photon anti-bunching, we have to calculate the Mendel parameter, and so basically we require these four things to compute, which is slightly complicated, but it is possible to do numerically. I have just shown one of the examples, but there are the threes, all the other threes have been constructed. This is the 80 square. Just for filling. Now let's look at the numerics. It's better. So we have analytics, but I mean, so let's. So the first two talks, plots are the squeezing, quadrature squeezing, and the last two are the photon anti-bunching or Mendel parameter. So what we see that in this case or this case, we see some of the regions, the squeezing parameter S1 goes to negative, like this one and that one. And also in S2, we see that they're going to the negative region. That means the squeezing does exist. And similarly, in the Mendel parameter, here always they're always negative. So there is no point, I mean, they're always squeezed in photon number distributions. So yeah, so far what we have seen that yeah, there is a squeezed atom laser can be constructed from this kind of system, but one might ask a question: what kind of system am I working with? I mean, this is a deformed relation, and what one can do with this kind of deformed system. So the motivation comes from basically the slightly of quantum gravity literature. What is the usual approach of quantum gravity? It is that people use the usual quantum mechanics to try to quantize the gravity, but there has been a lot of problem, and this is well known that this is not possible. I mean, almost every approaches of quantum gravity agrees that usual quantum gravity is not, I mean, usual quantum mechanics is not useful for quantum gravity, because in the ultraviolet regime, you cannot renormalize the quantum field theory. So what people does basically use some kind of deformation structures. For example, non-commutativity is one of them, which they use to introduce the cutoff. For instance, in the very first version of Snyder, where the commutation relations were introduced in the hope that they will be able to regularize the quantum field theory, and this is indeed the case. One has to put a cutoff into the ultraviolet domain, and that cutoff can come from this relation. And also there is this other version, Seiberg and Witten, which is very famous, and this comes from the string theory literature, that they want to introduce this kind of non-commutativity to get rid of difficulties they have in the string theory. But so the thing is, like now, so we have a non-commutative space-time which can circumvent some problems of quantum gravity. But then the natural question is that what happens in the quantum mechanics level or quantum optics level with that system? So, I mean, the approach is exactly opposite. So, people take quantum mechanics and try to quantize gravity. But if I take a quantum gravity model and come back to the quantum mechanics, we can see a deformed structure and try to see the consequence of the deformed structure. So that's how the model has been introduced. So there are more versions. This is called non-commutative phase space. In 3D, of course, so people have studied these kind of models, and there is a lot more simpler version, which is actually we are working, is just one-dimensional version. Of course, one can work in 2 dimension, 3 dimension, which we have worked out, but if we just consider the one-dimensional version, which is very simple, and the minimal length that can be calculated, which can be introduced in the ultraviolet domain to regularize the quantum field theory. Now, so what is the thing that is coming out of this study? So the thing, what we understand is that we get a nonlinear picture. We get a, if we take this model and go to quantum mechanics level or quantum optical level, we get a nonlinear picture, which is a quantum mechanics. There is no problem with the quantum mechanics. All things are preserved. Only a deformation parameter is coming and some deformation is understood. But this deformation, I think it is not so difficult to understand, because there is a experiment with the nonlinear theories, so one can just go back to this Hamiltonian I showed before, and then there is no problem. So so that's why we thought that we should study some quantum optics and quantum information theory, and we have studied actually quite a lot of model. For instance, coherent state, cat states, squeezed photon added coherent states, and so on. Many states we have studied, and we saw that actually there is no violation with the quantum mechanics, but we get additional degrees of freedom into the system. That means, for example, if we study the entanglement, quantum entanglement of the system, then we see that in case of usual harmonic oscillator, we have some quantum entanglement. Let's say we have some non-classical state, and we compute the quantum entanglement of the system. And we use the same setup to get this kind of model and try to construct entanglement of the system. We see always higher entanglement. And there is also 1 degree of freedom with respect to this parameter tau. If we increase the non-commutativity by increasing the tau, we see that the entanglement increases beyond the quantum mechanical level. So, so no problem, but we get a more freedom. So that should be interesting, and that's why. So in this review, we have actually worked out some problems, which, if you're interested, one might see. So with that, I will conclude. So the thing is that we have an alternative method to construct squeezed atom laser. And we have everything analytically, so one can just do whatever they want. Since the model is originated from the quantum gravity theories, so it might give some insight of a deformed quantum theory or a consistent quantum theory which is compatible with quantum gravity theories. And more importantly, this nonlinearity is the main key here. And this nonlinearity may be possible to understand in the laboratory. So it's, it's just nonlinear, so there is no problem. With that, I would like to thank you all.
Students?
Yeah, in one of your slides, you ignored or probably dumped those M dagger and all these combinations. Are you restricting to some Jaynes-Cummings model or something? I mean, what was the propriety in ignoring those things?
I didn't use Jaynes-Cummings model, but that can be studied. But we haven't studied with this. It's just usual quantum, usual coherent state we have constructed.
Okay, fine, thanks.
More questions? Okay, if not, thank you again.